welcome to this online revision session for AQA FP3, in which we'll be looking at the June 2011 question 7 on polar coordinates. As you can see, there's a number of parts in this question relating to two curves, C1 and C2, and their equations are given, the range of values of theta over which we're working. And then, first part, we have to change one of them from a polar to a Cartesian form. Second part, given the two curves, we have to find the points at which they meet and state the coordinates of the second point that we find. And then in part 2, from the two curves we have to determine a point on each curve and which one is further away from the pole. And finally we find a region, an area enclosed between these two curves. Okay, well, a number of parts of this question to work through. So the first part is finding the Cartesian equation of C1. So C1 tells us that R equals 2 sine theta. So we need to be aware of the fact that R cos theta is x and R sine theta is y, and also the fact that R squared equals x squared plus y squared. So if we multiply both sides by r, that creates an r sine theta and it creates an r squared. So we can then see that r squared is equal to 2r sine theta. And then we know that r squared is the same as x squared plus y squared. And r sine theta is just the same as y. So the right hand side becomes 2y. And we're not asked for the equation in any particular form. There is a Cartesian equation in terms of x and y. That will do just fine. And so the marks for that question, part of the question, will be a method mark for realising what we can do here, making this statement about r squared equals 2r sine theta, and then substituting in for r squared and substituting in for r sine theta. Each of those will give us a mark. So we've done them correctly. Okay, on to part 2. We're trying to find the points at which the two curves meet. So we've got r equals 2 sine theta and r equals tan theta. So we're going to solve those simultaneously so we can put them equal to each other. So immediately we can write down the fact that 2 sine theta will be equal to tan theta. And of course we can remember that tan theta is sine over cos theta, so if we multiply through by cos theta, we get twice sine theta cos theta, and that will equal sine theta. So now we can take that sine theta across to the other side and factorise the expression that we get, and so the sine theta will come out as a factor, and we will end up with 2 cos theta minus 1, and that will be equal to 0. Having got that, we can then see that will lead to two solutions. One solution is sine theta is equal to 0, which tells us that theta is 0, which is of course the point at which we have the pole. And then secondly, we get the fact that the cosine of theta in the bracket must equal a half, and if that's the case, that tells us that theta, remembering the range of values is between 0 and pi by 2, can only be pi by 3. So this is the second point P that we're interested in. Okay, so we know that theta is pi by 3, that's the angle. So we need to calculate the value of r. So for example, we can do the sine of pi by 3, which is root 3 over 2 multiplied by 2, so the r value that's corresponding to that point must therefore be root 3. Again, 4 marks for this part. So again, equating them initially will give us a mark, and then rearranging them and factorising this into an appropriate form as a method of solution will give you a mark. Obtaining the two values of sine theta and then realising that one of them is the pole, theta equals 0, and the other one is when theta equals root 3. And then finally your fourth mark will be for realising what the coordinate, the polar coordinate of P is going to be, and coming up with an accurate answer for that. And then in part 2 we need to determine the points A and B on each of these curves. So to determine the point A, theta is pi by 4, and the curve is r equals 2 sine theta, so we got 2 times the sine of pi by 4. Well, the sine of pi by 4 is 1 over root 2, so that gives us 2 over root 2, which simplifies to root 2. Similarly for B, it lies on curve C2. Again, theta is pi by 4, so they're lying on the same arc going out from the origin, and this time we got the tan of pi by 4, and the tan of pi by 4 is going to be is 1, isn't it, because it's pi by 4, 45 degrees, yep, it's 1. Okay, now since they lie on the same line, the values of r will then give you the distance from the origin, and you can see root 2 is bigger than 1. And if root 2 is bigger than 1, that must imply that A is furthest. Just 2 marks for this. So again, coming up each of these coordinates, I'll give you 1 mark, and then for making a statement that A must be furthest because the fact root 2 is bigger than 1, that will give you 1 mark there. Well, finally we've got to find the area of the region bound by the arc OP of C1 and the arc of OP of C2. So we know that one of these is bigger than the other because the point halfway along it is further away from the origin than the other. And so if we find the area bound by the first arc and the area bound by the second arc, then the area between them will be the difference in those two answers. So the first thing we're going to do is to find the area of arc OP of C1. Now we know that to find the area it's an integral of a half r squared d theta, so this becomes a half the integral. Well, r is 2 sine theta, so when you square that, that becomes 4 sine squared theta d theta. Now the limits of this curve are going to be between the 2 points at which they intersect. It's not between 0 and pi by 2. It's going to be between 0, because that's where it intersects, and pi by 3. We can divide through by 2 here to make that 2 sine squared theta. And then to integrate 2 sine squared theta, we use the double angle identity that because we know sine squared theta is a half 1 minus cos 2 theta, and so when we double that, we're just going to get 1 minus cos 2 theta. So this is going to become the integral from 0 to pi by 3 of 1 minus cos 2 theta d theta. And so, if we work that out, the integral of 1 is theta. The integral of cos 2 theta will be equal to minus a half of sine 2 theta. And that's going to be evaluated between 0 and pi by 3. And what will that give us? Well, substituting pi by 3, we're going to get pi by 3 for theta minus a half the sine of twice pi by 3. Well, twice pi by 3 is 2 pi by 3, but by the symmetry of the sine graph, we know that the sine of 2 pi by 3 and the sine of pi by 3 are the same, and they're both equal to root 3 over 2. And so when you halve that, that will become root 3 over 4. When we substitute 0 in, we're just going to get 0 minus half the sine of 0, which is also 0, so it's just 0. So this is the value of our first area. Now we need to calculate the value of our second area. So that's the area of the arc OP of C2. Once again, it's going to be a half the integral. Again, the limits will be between 0 and pi by 3, the beginning and the end, 2 points of intersection between the curves. And this time the function is r equals tan theta, so this will become tan squared theta d theta. Now to integrate tan squared, key thing to remember is we know that the differential of tan is sec squared, or the integral of sec squared is tan. So if I can rewrite tan squared in terms of sec squared, I can do this integral, and of course I can rewrite it because I know that 1 plus tan squared is sec squared, so therefore tan squared is equal to sec squared theta minus 1, using that identity. So if that's the case, I can now evaluate this integral, because the sec squared will become tan theta when I integrate it, because the differential of tan is sec squared minus theta, and that's between 0 and pi by 3. And so once again, if I put pi by 3 in here, the tan of pi by 3 is root 3. So this becomes root 3 over 2. And then I put pi by 3 in for theta, and I halve it. That gives me pi by 6. And again, if I put 0 in both places, tan of 0 and minus 0 is just going to be 0. So there is my area for the second loop between 0 and pi by 3. So the required area is going to be the difference in those two. And we know from the earlier work that C1 is going to be a bigger area than C2. So we can now do pi by 3 minus root 3 over 4 minus root 3 over 2 minus pi by 6. And if we simplify that, we got pi by 3 minus and minus pi by 6, that's plus pi by 6. Well, pi by 3 is 2 pi by 6, plus another pi by 6 makes 3 pi by 6, which cancels down to pi by 2. And then I've got minus root 3 over 4 minus a root 3 over 2. So the root 3 over 2 is 2 root 3 over 4, so that gives me minus 3 root 3 over 4. And that's in the required form of a multiple of pi multiplied by a multiple of root, or plus a difference of a b times root 3. Well, the allocation of the marks will be, I've got 10 marks to allocate here. So again, for substituting in to the correct formula to get the first area, will give you 1 mark. And then a method mark for then replacing the sine squared with the cos 2 theta. Being able to integrate that accurately will give you 1 mark, and then being able to evaluate that accurately will give you a 4th mark. Similarly on the second part, using the correct substitution will give you 1 mark, and then again you will get a method mark for replacing the tan squared with the sec squared, and then for evaluating coming up with the integral will give you 1 mark, and evaluating it correctly will give you another mark. And then finally, for realising that the area you require is the difference of those two answers will give you a mark, and then evaluating that correctly in the correct form will give you your final and 10th mark. Well, hopefully you found the solution to that question helpful. For more solutions and help with your revision, please go to the Further Maths Support Programme website.